omega squared plus 1/2 m v squared. It's r squared, omega squared is v squared. So when we set it up with it, we have a translational and we have a rotational kinetic energies, we actually just skip the step of this. Because if I think about it in terms of, I'm rotating about this point at the tip of it, or the bottom part of it, at this point of contact right there, it actually breaks down into the rotational kinetic energy rotating about the center, plus the translational kinetic energy. We could go one step further. I have a center of mass here, I have a force acting that way, I have a normal force acting this way, I have weight acting down. The friction and the normal force are not exerting any torque about that axis of rotation because they are acting right on it. It's like pushing on a hinge over a door. The only thing which exerts any torque is the weight. And so I could go through and calculate what is the torque by this, figure out the angular acceleration, and then do the problem that way. That is a longer process, so I won't go into it, other than just to say we could also have done it that way. Yes?
Can you restate again why friction and the normal force do not exert torque?
Because they're working from the center and not and like towards the round, but in a different way than like.
Is it wait? Is it because it's in the center? The pivot point is in the center.
There's a pivot point, friction's acting there. My moment arm is from the axis of rotation to where the force is applied.
Which is
So R would
Parallel?
be 0.
because it's
Okay,
parallel to the ramp.
R has a length of 0 and parallel perpendicular, not quite sure how much meaning there.
The friction force is parallel to the ramp.
Oh yes, friction force is parallel to the ramp. But the moment arm is 0 because the
Yeah.
force is being applied at the axis of rotation.
So it's basically infinitesimally small.
I would say even smaller, it's 0.
You're effectively trying to push the hinge, it ain't going anywhere. You're effectively trying to push the hinge, it ain't going anywhere.
Yeah, I'm trying to open the door by doing this.
Yeah, evidently so.
Like, questions before we start dealing with choices?
Yeah, why did you write the little bucket things on the bottom terms?
That indicate that starting with just the kinetic energy of rotation
Okay.
about the actual axis of rotation. That it just breaks down into the kinetic energy, the rotational kinetic energy if it's rotating about its center, plus the linear kinetic energy that we all know and love.
So rotational plus
Rotational plus translation.
rotational plus linear.
Why, when we're filling out the inertia, why do we just do I sub c plus mr squared if, like, why don't we do, if it's like a solid sphere, why don't we do 2/5 mr squared?
I could have done 2/5 mr squared for this, I just
Chose not to.
didn't feel the need.
So why is there another mr squared?
Why isn't there another mr squared?
Yeah.
This is the parallel axis theorem right here.
Oh, he replaced omega. No wait.
No, he
So
replaced
from here to
I.
here, the moment of inertia of a rolling object about this, some sort of round object about this point right here, would be
Yeah, sorry, I
Can you
completely
explain
forgot.
why you added the parallel axis theorem?
because I know, because for most objects, I know what the moment of inertia is if it's rotating about its central point. And here we have it rotating about this point right here, which I
Okay.
typically don't know. So I broke it down into, I used the parallel axis theorem because we moved the axis from something I would know to something I'm trying to figure out.
vantage point, which is something you have to figure out
So in this case, the edge.
to another point, basically.
Yeah.
Is that an F or some kind of weird E?
That's an F. This beam is in static, linear, and rotational equilibrium. In other words, whether it just is in there. I have this beam being held up by two forces at the locations indicated in the drawing. And the question is, what are those two forces?
What are
What does total mean in this case?
Linear equilibrium and rotational equilibrium.
Okay.
All right, so let's work through force. Let's start with the force diagram. Oh, assume the beam has uniform density. In other words, the center of mass is in the actual center of it. So we have two examples of other. I draw it somewhat similar to what I have.
And is force 2 right on the junction between 6 meters and 3 meters?
Yes. And then weight is acting down, let's see, that is 9 meters long, so that would be at 1.5, so I have weight acting down. Direction of acceleration, well, it's in equilibrium.
So when you're doing the other force, since it always comes in pairs, where would the compare to that be?
Whatever's holding it up, there's gonna be F2 and F1 are acting down
Okay.
from something. In a lab situation, they're force scales. They're holding it up and then the beam is pulling down the force scales. Coordinate system, I've already established that. Sorry to spoil that fun for you. And decomposition, no. All right, let's jump straight to the equations of motion. We have two unknowns, we need two equations. All right, what's one of our equations of motion?
F1 plus F2 minus weight equals 0.
All right, here's one.
There's another?
Excuse me?
There's another?
Yes.
Oh, wait a minute. That's for just J. I had.
All right, when we're dealing with equations of motion, and if it's all linear like we've done up till now, the sum of the forces, or the total force is equal to mass times acceleration. That's, the summation is understood. So the total force is mass times acceleration, that's what we've been doing. But now when dealing with rotation, we have torque is equal to I alpha. That is going to provide the next equation of motion. I know alpha is 0 because of the equilibrium status. So the sum of my torques is going to be 0. Well, to find the torques, I need to pick an axis of rotation.
Well, that's why I didn't understand.
There is no natural axis of rotation here. It's just sitting there being held up by two whatevers. Not like a door where you got a hinge and there's a natural place to pick it. So, what do we pick for our axis of rotation for something that is not rotating?
The middle?
Okay, anyone else?
Would that make things difficult? If we chose the middle?
You could also pick a point where the forces are acting.
Okay, anyone else?
And what was the question?
Where do we pick as the axis of rotation? So far, middle and where one of the forces is acting.
I kind of agree with doing force 2 as the axis of rotation.
Why?
Because it's the junction between 6 and 3, and that feels special to me.
Okay. Who do we pick the middle? Yes. Little musical interlude there.
It sounded like an ice cream truck at first.
So if you have no clear if the object is in equilibrium, and there's no clear axis of rotation, if there's no acceleration, rotational acceleration, you can pick anywhere you want. It doesn't even have to be on the beam. I can pick a spot off the beam. Now, typically, you would pick a spot that's going to eliminate an unknown. It makes the math slightly easier. Depends on how much math you want to do. Picking it where one of F1 or F2 is acting does make sense. Picking the middle is fine. But there seemed to be some more desire for it than lack of desire for it. So let's pick that. Now, I'll have two moment arms. I'll have a moment arm going from here, three technically. I'll have a moment arm going from here to where force 1 is acting. I'll have a moment arm from here to where the weight is acting, and then, I guess officially, there's a moment arm from here to where F2 is acting, but that's size 0. The sum of the torques is equal to 0. So let's go with, all right, let's think through this. The torque exerted by F1, is that positive torque or negative torque? In other words, is it pointing in the positive k-hat direction or the negative k-hat direction?
Negative.
Negative.
How'd you get that?
This.
So if you treat this as a pivot point right here, if this part is fixed, and then you push up here, which way will it rotate? Well, it'll rotate into the board, or R cross F into the board. Were you doing the which way would it rotate it, or R cross F? Okay. So it's going to be negative torque, as I said, out was positive. So negative R, I'll just call it R1.
Can you explain to me why, again, you want to put it at a force point because it removes something? What's that something again? An equation?
At a force point.
Yeah.
Because when I do out my equation, F1 is going to be an unknown, F2 is unknown, but if my axis of rotation is there, then F2 does not exert any torque. So it's not going to show up in this equation.
Remove an unknown. Or
Yes. Plus RWW
Okay.
plus 0 times F2. Typically won't write that, plus 0. So we have our J hat equation, we have our K hat equation, I hat equation if you really want to do it. Here's the I hat equation. A true statement, but not particularly useful. I know weight is equal to mg. Let's put this on Earth too. Meaning
Earth 2?
J G is 10 meters per second squared. So I have F1 plus F2 is equal to 50. I have negative 4 F1 plus 1.5 times 50 equals 0. Two equations, two unknowns.
How did you get negative 4 plus 1.5 times 50?
How did I get the negative 4 F1? Or you're quieter than my ears.
How did you get that last equation?
I'm plugging into here. The way I've written this is the magnitude of R times F1, negative. We've already determined the direction is negative torque. R1 is a vector from here to here, which is 4 meters, because that's 6 and that's 2, so that's gotta be 4. And so negative 4 times F1, and then the weight is in the center. So it's a 9-meter long beam. So therefore this is 4.5 meters. And so that has to be 1.5 meters.
Okay, I see.
And so F1 is equal to 75 fourths. Which is 18.75.
Wouldn't it be negative somewhere?
The force should be positive.
Never mind.
Okay. I'll talk about that in just a moment. I think what you're asking about there. And then from this equation right here, F1, or F2 is just the difference between F1 and 50. And so that'd be 31.25. Newtons. Let's just do a quick check. If we're treating the weight as acting at the center, it is much closer to F2 than it is to F1. Which means I would expect F2 is holding up more of the brunt of the weight of the beam than F1 is, so I would expect F2 to be bigger than F1. That works. I can do another check. I know since my axis of rotation is irrelevant,
How did you get F1 plus F2 equals 50?
the weight is mg, 5 kilograms, that's 10 meters per second squared.
Oh, okay.
If I pick this as my axis of rotation right there, then my torque would be 2 times F1, 18.75, unless I made a careless error there, minus 50 times 4.5, plus 31.25 times 6. Does that equal 0? If yes, then I'm feeling like we got the right answer.
Can I ask a question?
Yes.
kg times m over s squared is just n over s, n times
just
s
the-
squared?
A kilogram meter per second squared is a Newton, by definition of Newton.
Thank you.
And we will, yes, Abigail.
Can you explain how you got the Wilbur
It's the moment arm here. And the moment arm is from my axis of rotation, which we picked to be here, to where the force is applied, which was the middle. Is that, okay.
And that's just I, correct?
Just I.
Like the value I? What's the term for moment arm?
R.
R.
Yep, WR.
Thank you.
Now let's just suppose you get faced with a problem like this and you're going, all right, now I cannot remember what positive torque and negative torque. All right, relax. There's a different way of doing the exact same thing. If we go with our convention here, up, to the right, and out are all positive. Then if I did the sum of torques, and we're going looking at this situation right here. My moment arm is going to the left, which is negative. So -4. The force is up, so that's positive, F1, plus. Now, the weight, the torque from the weight, well, the moment arm is to the left, so -1.5. Weight is down, -50, plus 0 times F2 equals 0. If I'm choosing to the right in the nice horizontal vertical problem we have here, if I'm choosing to the right positive and up positive, I could just do it this way and not have to think through, let's see, is this gonna cause it to rotate clockwise or counterclockwise? It'll come out, you get the same answer. In the 110 version of the G2 Kabuko lab, this is the way, this is the approach.
Why exactly is the G2 Kabuko again? Can you explain why again it's G2 Kabuko?
I didn't explain before.
He watched it, it's like an old television show.
Yeah, I looked it up, it's a dude.
Yeah.
What does it refer to in this case?
You just didn't look far enough, all right? We'll see.